Hello and welcome back to Chapter 7. We're going to move on to talk about seafloor spreading. It's sort of the other half of the modern plate tectonic theory. It's together with continental drift, which was Alfred Wagner's hypothesis, really put together the modern theory of plate tectonics. Of course, it remains a theory because there are a lot of things that we just don't know or don't have answers to or aren't like really well explained. But so far to date, geophysicists, geochemists, paleontologists, sedimentologists, all of these different fields that study Earth or study the Earth are consistent in sort of the broad understanding of how it works. Harry Hess came along in the 1940s and just before World War II, and he was sort of thinking about how the Earth worked and plate tectonics, or at least continental drift. And it turns out he was in the military, and he was a troop ship captain, and so that means he was traveling around in the Pacific. He was dropping troops off near or along, shallow waters, and his ship was equipped, as many ships were, with something called a fathometer. And the fathometer was really just an echo sounder. It was a single point device that sent out a sound, and it bounced off the ocean floor and came back, and you could figure out how deep the water was, so you didn't run your ship aground. And Hess had spent some time as a geologist at Princeton, and so he was interested in what was going on the ocean floor. And so he's born at a time just before Alfred Wagner is coming up with his and presenting his hypothesis for continental drift, and Hess lives into almost the 70s before he passes away. His original idea was published in almost the 60s, so it took quite a long time for him to put it together. And the geopoetry is what he called it, because he didn't have a lot of evidence for it. But I wanted to talk briefly about geos and what he considered as evidence for seafloor spreading. This was later confirmed by a couple of geologists at Cambridge University by the name of Vines and Matthews, and I'll talk about their findings as well. So Hess's idea was, as he was driving around in the Pacific Ocean, captaining his ship, he found that they had areas of the ocean floor that were like mountains or topographically high. But he also found that in the deep parts of the ocean, on the abyssal plain, way out here, far from the ridge, he found these flat-topped seamounts. So there are, of course, lots of pointy seamounts on the ocean floor, little volcanoes that have emerged, and then you have the mid-ocean ridge itself. And his idea was that these flat-top mountains had once been up on the ridge and close to the or even above, really, the ocean water level, and that once they had gone extinct as they had moved down with the ridge and off the other side like this, that they had been planed off and the top end had been cut off to make them flat. And so his suggestion was that the seafloor was moving, that these things were once at higher elevations and had moved off of this mid-ocean ridge, which we knew was down on the bottom of the ocean, but what was going on there, no one really investigated yet. And so that was his geopoetry, his explanation for how the seafloor moved. Now, the advantage of this is that it didn't require the continents to collide with oceanic crust. Of course, it meant that the crust itself on the ocean floor was moving, and one would maybe then infer that the continental crust and the oceanic crust were moving together. We didn't really have great evidence for this until we started investigating the magnetic seafloor anomalies that were something that Vines and Matthews were testing out. And what they found and they were actually it's an advisor and a student working at Cambridge. What they found was that people had studied the ocean floor, and we knew that the Earth had a magnetic field, and that rocks were recording the magnetic polarity, the positive or the negative polarity of Earth's magnetic field, and that at times, in some cases, the field entered at the North Pole and exited at the South Pole like this. But then also that could be reversed, and that there were also times when the polarity was reversed, and the field would actually exit at the North Pole and enter at the South Pole. And today we still don't really know. We can't predict it, and we don't really know exactly what's going on there, except that it's probably related to convection in the outer core. But that this resulted in a kind of magnetic sequence of rocks on the ocean floor. And so that's what these dark and light lines are on this diagram here. They represent the magnetization of the rock. So the rock is uniform in color, it's uniform in shape and size and texture, right? It's oceanic rock. It's not anything special. But when you run a magnetometer over it, you find that it's different, and it's different in the magnetic polarity. And so we have a negative anomaly here, and then we have a positive anomaly right here. And so that's where the magnetic polarity swings in one direction, and it swings in another direction, and it swings up, and then it swings down. Okay, and what Vines and Matthews did was they looked at this on the ocean floor, and they asked questions about it. Why is it symmetric across the ridge? Why are these boundaries in here? Why is there a line parallel to the ridge? So right, the magnetic anomaly is a stripe. Why is it striped, and why is it parallel to the ridge? We couldn't quite figure out the sequence of flips, because you'll notice on the left-hand side here, we have all of these ages, and we name the ages of these different flips or these different events based on who found it and who identified it, or sometimes like where it was found, right? But they are very short or they're very long. So that part is still a kind of a mystery to us today, but it's the fact that they found these stripes, and that they were able to correlate them, and they were able to correlate them with the magnetic layers or the magnetic anomalies in the layers of standard sort of terrigenous volcanoes. So the volcano is easy to get to, right? You can go up, you can walk up to it, you can drill a hole in it, take a sample of it, and you can get a date on it. And so that means you can get a numerical age, right? So they got numerical ages on these volcanic deposits, and they also got or measured their magnetic polarity, whether they were normal or they were reversed, and they came up with a kind of time-lapse sequence for the positive anomalies and the negative anomalies and the positive anomalies for this volcano or a series of volcanoes. Then they took this map and they laid it on top of, if I go back, of the map of the ocean floor, and they were working off of the Juan de Fuca Ridge in the Pacific Ocean primarily. They laid it on top, and they found that it matched up. The times for these at these boundaries, so if this is, let's say, time 0 where spreading's going on, this is time 100 or 1 million years, and then you find 1 million years out here, 2 million years out here, 2 million years out here. You found that the oceanic crust got older as you moved away from the ridge, and they found that the sequence of polarities, flips or reversals, lined up perfectly with the terrigenous polarities as well. And we came up with a map of the ages of the sea floor, and they helped to confirm that the youngest crust was always on the mid-ocean ridge. I should draw that in a slightly different color probably. All this diagram has all kinds of colors on. There's the mid-ocean ridge, and that's time 0 at the mid-ocean ridge. It's the youngest material here, 0 million years, and then every ocean has one of these kinds of mid-ocean ridges running through it. And then as you move away from the ridge, the oceanic crust gets older. And so we confirm this by drilling into the crust, and we can radiometrically date it. But it's a lot easier to drive your boat over this thing with a magnetometer, excuse me, and figure out where those polarity flips were and then match them up. What's interesting to note is that we always find that the oldest oceanic crust, which is no older than late Jurassic, so we're not getting any older, way out here, it's a little older than 150 million years. It might be 190 million years. We don't really find any oceanic crust older than that. And the oldest oceanic crust is always attached to the continents. And so here's old oceanic crust, and here's old oceanic crust. And the youngest stuff is always attached to the mid-ocean ridge, or overlaps with the mid-ocean ridge. And it also turns out that we find that the most crust, the widest swaths of young crust, if you will, or the widest swaths of crust of a certain age show up where the spreading rate is the fastest. So notice how wide it is here in the late Cretaceous. Notice how wide it is here for the Miocene. Come over to the right-hand side out of the Pacific and into the Atlantic Ocean. So here's the Atlantic Ocean. Notice how thin that Miocene is. Notice how thin that the Paleocene or the late Cretaceous is, or even the middle Cretaceous right through here. And so this is a slow spreading center in the Atlantic here. And if you come over to the Pacific Ocean, over here you've got a fast spreading center, spreading at probably around 15, 16 centimeters per year, whereas the Atlantic Ocean is sort of 2 to 5 centimeters per year. What this allows us to think about, too, is the nature of oceans and the formation of divergent boundaries. Oceans are born. They're formed in places where the crust is separated and actively rifting. If you're interested in where are there rifts in the crust today, East Africa has an active rift today, and it'll probably sort of die out eventually, but it comes down like this, and then there's the Red Sea right up here, and the Gulf of Aden comes off. In North America, we've got Lake Superior, which is an extinct rift. It is no longer active, but it's a billion-year-old rift that would have, if it continued, probably ripped North America in half. But for reasons that we're not really sure, it stopped, okay, and left a low spot that ended up becoming Lake Superior. The Rio Grande Rift down in New Mexico is a topographic low spot that is no longer active, but was the source of a lot of volcanism that started around 36 million years ago, and today remains fairly hot, although excuse me, as rifting has likely stopped in that area, we don't expect it to continue on. But the basic sequence here is that the crust is going to be pulling apart, one side going to the left, one side going to the right. And as it does so, this center part gets really thin. And as it gets thin, it allows the asthenosphere to rise up. And as the asthenosphere is rising up, that allows the hot rocks to touch the cooler rocks and to cause melting. And that produces volcanoes and volcanism in this area. So we expect calderas and cinder cones and all kinds of different volcanoes to be formed in this region. And if you indeed go to look at the rocks in New Mexico, that is what you find in what is essentially a kind of failed rift. Now, what happens when the crust keeps pulling apart and eventually you break through and thin the continental crust as thin as it can go? Well, it doesn't just make a hole in the ground. We have to fill it with something, and so we start to fill it with oceanic crust, and that's what's coming in here. Oceanic crust is being filling in this space, and also what's happening is, as things get so thin, the topography goes down. The Earth's crust sort of sinks in this area, and that allows the ocean to come in. So that allows the water to come in, and so this is roughly what the Red Sea is today. not the Reed Sea. It's the Red Sea. Oh, look, it's in red. The Red Sea. Red? No. Oh. Red Sea. We'll get there. the Red Sea is today. But if you allow that Red Sea to continue to spread, you're going to end up with something like this, where we have oceanic crust, which has continued to sink, and that's because it's cold and it's dense. When it comes off of the ridge, we'll see the shoulders of the passive margins wear down with through erosion over time. And so we get sort of gentle slopes as we come off of Africa, which might be over here, and we come off North America, which might be over here, or you could also do South America as well. And this is more like the Atlantic. So the Atlantic Ocean is a mature ocean basin that formed when Pangaea rifted apart. The process usually, as we understand it, starts with some sort of hotspot or plume, and that plume creates a kind of dome, as you can see here. And then rifting involves 3 arms. This is a kind of energy minimization situation, a stability issue, where we end up with 3 divergent boundaries all connecting at a central location. And so if we bring that down here, here's the Gulf of Aden connecting with the Red Sea, connecting with the East African Rift. The East African Rift is now what we're going to consider an allocogen, A-U-L-O-C-O-G-E-N, allocogen. It's still active. It's still seismically active. It's still sort of spreading, but it's much more slowly than the Gulf of Aden or the Red Sea, and so it is likely to be the what we call the failed rift or the failed arm of rifting. But research down there is in that area is ongoing, and so I think it's sort of the active place to test this hypothesis for 3 divergent boundaries coming together, one of them failing. Excuse me. And so that brings us to the modern picture that we see today that I showed you here, where we've got crust separating in this direction and in this direction. We've got crust also spreading here because there's a spreading center down here like this, and then also spreading going on like this and like this. So we've got these 3 plate boundaries coming together at the center there, right there, and you can see there's a lot of volcanism, so you can see volcanoes and you can see rift valleys. And in fact, there's people off on the far right here. You can see right there are people, and there's a huge crack. That's a pretty unusual kind of canyon or structure, but it's the kind of structure you see at a divergent boundary. Where you get basically a big hole that can kind of open up in the ground. And that sort of summarizes the seafloor spreading hypothesis and the birth of an ocean. We'll move on to talk about the sort of anatomy of different kinds of plate boundaries, what kinds of features we'd expect, what kind of processes are going on, and then wrap up with a summary of plate dynamics